So basically, our equation d sine theta is equal to some multiple of the wavelength. If we have a situation like this, where we have double slits, this works for double slits or multiple slits. It doesn't matter how many slits, as long as we have at least two. And if we have this distance A, this distance B for the n equals 1, and this angle theta, then we know that theta is equal to the inverse tangent of B over A. And we can solve for this distance. D sine theta is equal to n lambda. D is equal to thus n times lambda over sine theta. And we know that theta is equal to the inverse tangent of B over A. And in a double, so this works for double slit, multi-slit, multiple slit, multi-slit, or diffraction grating, are other names. And the reason this works is that we have a point here. Light that is going from here takes a longer path. And basically, we want the extra distance to be exactly one wavelength higher. You want this bottom path to be increased by one wavelength for it to reach here. Obviously, if we do n equals 2, it'll be 2 wavelengths. But we want the distance between these two lines, or the length of these two lines, to be a multiple of a wavelength apart. So this one's longer. So this is going to be some x number of wavelengths. This would be some x number of wavelengths plus n number of wavelengths. Question. So this works because we have two pathways the light goes through. Can this work for a single slit? It can. So on the opposite side for double or multi-slit, we're going to have a stream bright spot right in between the two slits. Then we're going to have a lighter dot here, a lighter dot here, and then it's going to continue like that. In this case, we also have, so basically light's coming in and hitting here. We can imagine every single point of these being an infinite number of slits. Kinda. We can think of every single point as light spreading out from it. And there's going to be some interference as it goes through a single slit. However, the equation doesn't change, but the interpretation for the equation does. For double slit, multi-slit, diffraction grating, N corresponds to maximums, bright spots. So if I were to draw the intensity, I just realized how slanted this was. we can see here is n equals 0, n equals 1, n equals 2, n equals -1, and n equals -2. But the bright spots correspond to our n. From the middle of the slit here, we're going to see a humongous bright spot, as most of the light is able to travel through this hole. We're still going to see a diffraction grating. However, the angle is going to be to the dark spots, where there is no light. So for single slit, we have the same equation. D is now the width of the slit. So for here, D is distance between slits. It doesn't matter how big slits are. Here, D is the width of the slit, how big the slit is. And N corresponds to the minimums, are the dark spots. You good? So we can see here it's a multiple of n, obviously it's 0, but there's overlap. I'm trying to find a good picture. The more narrow the slits are, the better the image is too. Less blurry. So here's a double slit. What's this blurry? If we look at the single slit over, so if we were to replace this with single slit, then this single slit will basically touch all these peaks. So if we remove all the barriers in between and just have it have a single, this whole thing being a single slit. But this is basically how bright it is, how bright the dot is. So we can see that very bright under here. Right here will be a dark spot. This is slightly inaccurate. As it should look more like this. It gets darker and darker the farther away you get. Another thing they're doing here, you might notice, is there's no sign. Where'd the sign go? Do you want to remember? Or can you remember? What is something I told you can do with sign that engineers do? You should never do it in this class. It's like the very first thing I talked about. If we graph sine, and then we graph x, x and sine of x are approximately equal if x is significantly less than 1. And that's for radians. So significantly less than about 20 or 45 degrees. So obviously 20 degrees is not significantly less than 1 radian. That you cannot approximate. But most of the time, whenever they do diffraction gratings, it is over very small angles. I'm trying to find... this was it. That's how you can construct the right angle out of it. I'll actually show you how to do that. So looking at this, really the way to do it with high school math. So we have the midpoint right here. This would be n equals 1. So what I'm going to do is draw a perpendicular line right here so we have a right triangle. This hypotenuse will be D. And we have some angle right here. It's roughly or approximately beta. So this angle right here is approximately theta, which means this angle right here is theta. And thus, to get the length of this portion, again, this is approximate. I think this whole equation is approximate, but you get more accurate the smaller the angles are. So, this is the extra distance of this line right here. Can you see that? This line is longer by this amount. And since this is approximately theta, that means the length of this line, so that's opposite. So, sine of theta, this angle, is equal to opposite, which will be this. And we want it to be some multiple of a wavelength divided by the hypotenuse. And then rearranging it, we have d sine theta is equal to n lambda. That's how you do it using high school trigonometry, or as much as we get in high school. We just draw a line here. This turns it into a 90-degree angle. And we have a right triangle. We can use standard trig. So this is for single slit. Not save. So this is for single slit. It's for minimums. That's the difference between single slit and more than one slit. Is the n corresponds to minimums. And if we replace this with multiple slits in between, you'll see that the intensity brights are just cutting this off. Basically, we're cutting it up into different chunks. They usually use A to represent the aperture width, the width of a hole, by like keeping D, because it keeps the same equation. I want to go over thin film interference. Have you ever heard of the oil drop experiment? Don't do this, as it could damage the fish in the lake. It's not important for this class, but I wanted to illustrate how thin this gets. The first time we measured the width of an atom, we didn't really measure the width of atom, but we got close. What we did is, what's the volume of a cylinder? Has a radius R and a height H. What's the area of a circle? Pi R squared is the area of a circle. And now what's the area of the cylinder? Yes. Just like whenever you're doing the area of a cube or something, it's the area of base times height. So, what would happen if we knew the volume of a drop of oil? 1 milliliter. And what happens if we put soap or oil in a lake? So we have this humongous lake, and we put a single drop. Due to molecular forces and water surface tension, the oil drop is going to spread out as much as possible. It almost turns into a perfect circle. It's going to try to turn into a perfect circle. Except for this circle is extremely thin. Has a radius R, it's basically a cylinder, and the height is a few molecules of oil, few molecules of soap. It actually gets down to only a few molecules in width. It's a very, very thin layer. You could then, if you knew the original volume of the oil, even when it spreads out, the volume's going to stay the same. You can't magically change how much oil you have. Or soap. Soap works the best. Like this soap. And thus, you can figure out how wide the molecules are of the soap. Approximately, you'll have about 10 molecules or so. You'll get within an order of magnitude about. But imagine we have some water and a thin layer of oil. Light is going to come down here and strike the surface of the oil. What is the light going to do? You can do one of 3 things, but we'll ignore the third one. You can do reflect. So it's going to reflect off. So reflect. What else can it do? Absorb, we'll ignore that. It can go through, and when it goes through, it refracts. So this is going to be air to oil. Oil has higher, obviously. High index, low index. So which direction will it bend? Or draw this normal. It will go either toward or away from it. Towards. So it'll bend like this. And it's now at the boundary of oil to water. What's it going to do? It can either refract, depending on whether or not the oil has more. Most of the time it won't refract. It will reflect. And then obviously it can refract again, or it can go straight through. What do you notice? What about the length of this line versus the length of this line? Top line's longer? Are you sure? I mean, including this path too. Including this whole path, this could be a multiple of a wavelength off. This is called thin film interference. Remember double slit? double slit, we have it taking this path, and then it's taking this path, and we basically have, drawing this right angle off of it, we have this extra amount, right? So this is extra amount. And if this extra amount is a multiple of a wavelength, we get a diffraction pattern, we get a bright spot. If this is a multiple of a wavelength, we get a bright spot. You have no doubt seen this effect. So the thing is, usually we aren't using lasers. What are we mostly seeing when you walk outside? White light. What is white light? White light is all the colors, all the visible colors combined together. So you saw those dots, right? So when we did the multiple experiment, we saw a bright green dot. So only green could appear right here. And we saw other bright spots. Note, this whole thing is completely removed. So green does not start repeating until a very large distance away, right? So that means that all the green light between it is deconstructively interfered. So between the 2 points, there is no green light because it's been destructively interfered and cannot exist there. It only exists at the point of constructive interference. Look what we have here. We have a drop of gas on the concrete. That gas is going to spread out and form a very, very thin film. We notice that yellow only appears a certain distance away, but it's white light, so it's continuous. We'll notice blue only appears a certain distance away, the same distance. We can see red a certain distance away, but we now see it continuous because we see the rainbow. Soap bubble. Again, very thin film. Here we have air, soap, then air again. But all we're looking at is the time it takes to go through the soap or the oil and reflect off. This is due to interference. It's very similar to...
Jalea Mitchell, come to the office to leave. Jalea Mitchell.
Oil has higher index than water. So actually, I think at this point it's at the critical angle. No, it's not. No, it wasn't. You can still see through it. I'm trying to look. I'm not gonna have you do any math with this. What are they using Oh, they're using cosine for this angle, which would be sine of that angle. So T is the width, the thickness of the oil. You can also get a glass plate. It's also when you look at a CD, how you see like the rainbow effect in it, or anything like that. Trying to see if we can find a equation for this. I never had anyone do homework over it. Thin film interference equation. It's 2nd cosine. Oh, second. What is it? Did you ever do the homework?
I'm trying to stay home, but they wouldn't let me. Mom, they didn't do it.
Yeah, the equation is more complicated. It's not that much more complicated. I've just seen a little not written anywhere very neatly. Because I'm assuming it's on index of refraction. I think that's mostly it for the day.
Writing's not that easy. But Grammarly.
You should also be very careful when working with going between different materials, as the wavelength changes of light. The frequency stays constant, but the wavelength changes.